for having me give the seminar and letting me discuss my research. Yeah, I'll be talking about NASA satellite data, but first I'd like to thank my collaborator, Susan, has provided some input here, and also my collaborators at Argonne National Lab for most of the funding for this work and for a helpful insight on this. So let's get started here. Hopefully this will go. There we go. All right, so why I study air pollution. So I'm going to be talking about three of the most studied air pollutants: fine particulate matter, ozone, and nitrogen dioxide. Why do we want to look at the concentrations of these? Well, because they impair cardiovascular function, leading to these cardiovascular disease and premature mortality. It also causes, all three of these pollutants cause and exacerbate asthma. Particular NO2, in addition to sulfur dioxide, contributes to acid rain, so that that harms the ecosystems and also can harm our monuments, which is important around here. It impairs natural visibility, and then ozone in particular can stunt the growth of plants. So this is really important for the agriculture industry. So there's lots of financial losses due to ozone when it comes to growing our food. And then finally, ozone is a greenhouse gas. So it's approximately a third, the third most important behind carbon dioxide and methane. But it's really important to note the last box on the bottom here. Controlling air pollution in our economy costs billions of dollars. So that's with a B, lots of money. But the benefits are actually even larger. So the ratio, one of our recent EPA studies quantified that the cost in attaining the ozone standard, so there's many cities in the United States that are not attaining the ozone standard. For them to get into an attainment would be approximately $1.5 billion. So that's a huge cost, but the benefits, the health benefits from that, are on the order of $5 billion. So it's greater than 2, certainly. So there's a good reason why we want to control our air pollution. There's a recent study called the Global Burden of Disease. They've actually quantified air pollution globally. And I'm just going to show the statistics for the United States here. In the U.S., fine particulate matter, solids suspended in the air, very, very, very small solids, are approximately 88,000, responsible for 88,000 premature deaths. Ozone is approximately 11,000 to 12,000. If we just do a quick calculation here, there's about 2.8 million deaths, all cause. If we do this calculation, outdoor air pollution is responsible for approximately 1 in 26 deaths in the United States. I just looked up this morning how many premature deaths due to car accidents, and that's about 35,000. So outdoor air pollution is about 3 times, it causes 3 times more premature deaths than car accidents. So that's kind of a good comparison to show why we need to control our air pollution. Recently, Susan published this paper looking specifically at asthma incidences globally. Looking at ozone, approximately, there's error bars here, but approximately 15 million annual asthma emergency room visits globally. Particulate matter, again, the small solids suspended, are approximately 5 to 10 million. And the anthropogenic part, so not all air pollution is anthropogenic, but the anthropogenic part is a significant fraction of both for the ozone and the fine particulate matter. So certainly, and this is just on asthma incidents. These are emergency room visits. Of course, this doesn't account for daily, asthma attacks where there's no ER visits. There's also nitrogen dioxide can also cause asthma, in addition to exacerbate it. This is a recent paper published this year by Susan's postdoc, Chloe, former postdoc now. She quantified that approximately 4 million children develop asthma each year globally. This image is not weighted based on population, so of course the countries with the largest population have the largest values here, so I wouldn't focus on that too much, but just the overall value that 4 million cases children develop asthma each year, and NO2 is probably the easiest pollutant to So these are avoided issues that can be avoided with proper control. All right, so that's why we want to study air pollution. Let's get very quickly to the chemistry of it. It's going to be very, very brief, very, very high level. So a lot of our air pollution comes from both cars and power plants. This is very generalized here, and they emit NOx. And so any type of high temperature fossil fuel combustion will emit NOx. And so that's a primary pollutant. You're going to see very high concentrations if you go outside here on the roadway of NOx. But in the summertime, there's some complex chemical reactions, which are very generalized here, that can create surface level ozone. So you need sunlight, you need some actually emissions from trees, and there's some in the form of volatile organic compounds, and that can create ozone. And ozone is really what's going to cause these poor air quality days. In the summertime, you see an ozone alert or a poor air quality alert. In the summer, it's most likely due to surface level ozone. And so this is what's called a secondary pollutant. So it's not emitted from a tailpipe, but it actually reacts in the atmosphere with other pollutants. Also can be natural sources and creates ozone. So we really want to try and control our NOx emissions. So how do we typically measure outdoor air pollution? So actually for 3 years during my graduate work, I was the primary site operator at this site. It's in Beltsville, Maryland, about half an hour away from here, near the Baltimore-Washington Parkway. And this is actually one of the most comprehensive air quality monitoring sites in the country. It has a bunch of different monitors. So this is what an air quality monitor looks like. It's actually a box. And there's a couple of things in there, but essentially, it can measure the concentrations of air pollution. I can get into details if people are interested in how it works. But so there's several of these types of boxes that measure the gases in the air. And then there's also, at this site, there's a filter paper that actually collects the particulates, and then it's sent off to a lab, and you can see what types of particulates are in the air. We also are collecting at this site, or I was collecting, and I'm still collecting rainwater. So you collect the rainwater, you ship it off to a lab, and you see how much acid rain is falling. And then there's also a couple of, there's this what's called the deposition monitor here, where you're analyzing the stickiness of the gases. So how quickly is the pollution going into the grass or the vegetation. So anyways, there's approximately 1,000 of these sites across the United States. There's 6 sites within DC city limits. But there are, even though we have 1,000 in the United States, which is quite a bit, there are gaps in between. And so this is what the network approximately looks spatially across the eastern United States. So there's going to be a lot of monitors near the cities, and not too many monitors where there are no cities, which is good and bad, and I'll get into that in a little bit. So the EPA standard for ozone is very complicated. I'm trying to, I've simplified it to what's called an ozone design value, and this is what the regulatory agencies call it. And anything above, and then these colors don't particularly show up super well here, but anything in orange and red is above the current EPA threshold, and anything in red is significantly above the EPA threshold. And that's called moderate non-attainments. These are all lawyer terms that you don't need to know, but anyways, you really just want to focus on where's the red and where's the orange, and then also the yellow is, they're just below the threshold. So, if there's a change in pollution, it's very easy to go from yellow to orange, and then you'd be in non-attainment of the standard. So this is this current year. So we're still this is still an issue across the entire eastern United States in controlling our air pollution. All right. So here's a look at the trends. I didn't want to quiz you, but it's sometimes surprising to see that the trends in air pollution are actually going down over time. If I take someone off the street, they might think that the air pollution is actually getting worse over time, and it's actually getting better over the last actually 30 years really, but here I'm just showing the last 10 years or so. And the interannual variability has to do with two things. One is the meteorology. So on a very hot year, so 2011 and 2012 were extremely hot years around here, and so therefore the pollution was much higher than the mean here. So if we do a line here, you can see obviously that those 2 years were much higher. And conversely, 2013, 2014 were cooler than average years, so they're going to be below this mean. Overall, obviously, you see a decline over time, and this is obviously good news. And in fact, this past year, 2019, this is preliminary data, actually is the cleanest overall for the entire Eastern United States over the past 30 years, going back at least, since the EPA has been monitoring ozone. So this is great news that we're getting there, but of course there's still several areas in the Eastern United States that are above these thresholds, and so that's, there's still work to be done. Okay. And then let's take a look at air pollution globally. I just took a quick snapshot this morning of this website here. This data is not quality controlled, so you might see some weird values some places. That's to be expected. There's some issues with these sensors, but overall you could see the general pollution across the globe here. The United States generally right now has pretty good air pollution, low concentrations of many pollutants, primarily because it's the winter time and we've had lots of rain around in the eastern United States, so that's really what's driving the green over here. If you look towards China and India, you see obviously higher values, can be 10 times higher than the United States. So this is just a quick snapshot of what the pollution looks like, but as you can tell, there's several areas where there are no monitors, particularly South America, Africa, and northern Eurasia, Russia area. So this is where satellite data can be really helpful, but it can also be helpful in the United States as well, in between the monitors, and better quantifying what's going on, even a few kilometers away from a monitor where there really is no actual ground truth data. All right, so what does satellite data, or what do the satellites look like? So there are two types of satellites that are currently in orbit. There's one that's geostationary, and then there's one called the polar orbiting, where it goes over the poles, but it's a low, another term is low Earth orbiting. So geostationary stays affixed to one spot over the entire globe, so this would be great for if you wanted, say, like to monitor the weather just in the United States, or for example, if you want to spy satellite just the Middle East, that we'd want a geostationary satellite. For polar orbiting, that's more useful for NASA to gather entire global data, because it has a snapshot of everywhere over the globe once per day. So it depends on what you want to quantify here, but a lot of the satellites for Earth science are actually polar orbiting or low Earth orbiting, and it's great because it gets a global snapshot once per day, but it's also an issue because it only takes a snapshot once per day. So sometimes you ideally you want multiple of these satellites, so you have one polar orbiting and one geostationary, and I'll get into that a little bit later. All right, so what does NO2 from space look like? So here's an image from a new satellite just launched called Tropomi. Well, just launched in space. Anyways, it's been in orbit for 2 years, and that's very recent for a satellite. So this is what it looks like. It's the resolution is about 4 kilometers. Each pixel is about 4 kilometers. So you're not going to get a street, a different pixel here versus across the street. You're going to get, a single pixel over 4 kilometers. But it's, it's pretty good. You can get nice variability. You can pick out individual cities, obviously San Francisco, LA, and then a couple of the cities in the eastern United States here. So what it's giving us is realistic. An issue with satellite data is they can't peer through clouds. So this missing data right here, this is a day in September. It was cloudy here. It was actually a fairly sunny day across the United States. So we actually got a lot of data here. But So this can be helpful, but it's not as helpful as if we average over a very long period of time. And so here I'm taking a 2-year average of satellite data. I showed this in the first slide here, but now I'll explain it. So here's a 2-year average of NO2 from satellite data, and now we can pick out each individual major city across the entire United States. And then also you can compare the magnitudes. So, for example, like Denver, the magnitude of Denver versus Chicago, or New York versus Dallas, for example. And so this is really helpful in quantifying, where is our pollution coming from, but then also what, from a per capita standpoint, like how much pollution is coming from each individual city. And so this is quite amazing, at least in my opinion, that we can really start to see some small scale features, such as, this is a river valley in Idaho, where most people live in Idaho and do and there's agriculture here versus the mountains. So you can actually start to see these nice these ratios between areas that have emission sources and areas that don't have emission sources. So I've been using this data here. Let's just zoom into the Washington, D.C. area, since I'm sure that's of interest to most of you. So we can obviously see the 3 largest cities in our area: Philadelphia, Baltimore, and D.C. It's interesting to see that the pollution in Baltimore is worse than D.C. There's a couple of reasons for this, but I won't get into that now. It's also interesting to see the Dulles Airport area, which is a secondary maximum away from the city. So in previous satellite data that had very coarse resolution, you would just see a single blob of pollution coming from this area. And so that was helpful in knowing that you had pollution in this area, but it wasn't resolving the spatial heterogeneity. So again, you can kind of see the I-270 corridor. You can see I-95 connecting the 2 cities. You can also see smaller cities, such as Hagerstown and Frederick. So this is really exciting that we can quantify this variability in such a small area from satellite data. So I've been working with this recently. And so I've actually quantified the emissions from these cities, from actually three cities here in a paper just published, although I'm working on other cities and other areas, applying this work to other areas as we speak. But for right now, this is what I've been published in the literature for these 3 cities: New York City, Chicago, Toronto. And I was able to quantify how much pollution is coming from these cities. So EPA is reporting the bottom up. This is what EPA reports. They take all the traffic data, they take all the data from power plants, and other sources, and they calculate, so what's being emitted, and this is the value for New York City area. And so that's what EPA is reporting versus what I am using the satellite data to quantify, and that's about 18 micrograms per hour versus what the EPA is suggesting. So in this particular case, the EPA is actually overestimating what's coming out of tailpipes and emission power plant stacks. If we focus now to Chicago, it appears that the EPA's methods are actually quantifying the pollution pretty well. Again, we're seeing pretty good agreement between these two, which is good. And I also did this for international city, Toronto. We've been working actually pretty closely with Environment Canada. So they're really interested in seeing what's going on in that area. So I see a top-down using satellite data, about 14 megagrams per hour versus the EPA, or their reporting of their federal agency reporting of about 11 megagrams per hour.
Of NOx, is the satellite, probably no way to distinguish between the natural, but the EPA's bottom-up approach would not include the natural sources.
Correct. Yeah, I have a statistical method that filters out the natural sources, the background sources. So yeah, I'm not including that in this. What's nice about using the satellite data is actually we can report those emissions very quickly. Quickly is a relative term, but within a month or 2 of the satellite overpass, you can take some calculations to do this. But we can release these estimates fairly rapidly versus EPA. It actually can take them 2-3 years to release emissions data. So just having a very quick estimate of what's coming from these cities can be really helpful to regulators to see, well, how is this year's pollution versus last year's emissions. So that's really helpful for a lot of regulators, but also forecasters, for example, who are trying to estimate the pollution, the forecasting pollution. There's a couple of disadvantages, and because it's kind of a rough and quick calculation, these estimates are aggregated over entire cities, so we're not going to be able to distinguish, say, cars are in particular overestimated, or industry, or like construction, or vehicles are responsible. The satellite data cannot do that. And then also, if there are discrepancies, for example, in the case of New York City, it's hard to ascertain why that's the case. And so, of course, this is just one step in a larger, research topic of trying to quantify what's going on with air pollution emissions. So, perhaps you're wondering, how do you know that my method works? So you might be thinking about that, and I'll just put this up here. Actually, it works very well when we look at power plants. And so power plants have monitors on their stacks, and they quantify the emissions of air pollution very well. It's, of course, required by EPA. And so, for example, this is a power plant in New Mexico. This is a power plant in Montana. I'm taking a very isolated power plant so that we know that the satellite data is quantifying only that power plant and no other sources. And so, for example, this is the reported emissions from the power plant, and this is what my method is showing. So, with agreement within 10 to 15% for this particular power plant complex, and actually under 5% agreement for the power plant in Montana. So, certainly, I think. And this is really attributed to the satellite data itself. I mean, of course, I think my method is good, but it's really because of the satellite data. The satellite data is really amazing. It's actually the product is released by the Netherlands Meteorological Institute, and they've worked for 5+ years on this particular algorithm. So this algorithm is really great, and a lot of the, if you want to say the satellite data is good. Give them your props. So. All right. Another thing that we can look at when a satellite data is to compare the weekday versus weekend emissions changes. So, as you might know, I certainly know, is car traffic is going to be much worse during the weekdays versus weekends. And the satellite can see this, and it's pretty cool. We can see that the emissions on the weekdays are approximately 40 to 50% larger than the weekend, and this is mostly due to car traffic. And I can get into that as to why, but how we know that. But it's interesting that this actually agrees with what the EPA is showing pretty well. So this is one area where the EPA is reporting that emissions are about 40 to 50% larger on the weekdays, and we are using the satellite data to confirm that. So that was interesting. Another thing that we can do with the satellite data is actually estimate carbon dioxide emissions. And these are anthropogenic carbon dioxide emissions. It's hard to quantify actual CO2 fluxes. That's a whole different research topic. But here I'm just quantifying carbon dioxide emissions. So the way that we do that is we know that for every mile a car travels, for example, we know approximately what the ratio of NOx to CO2 is, and we can aggregate that over the entire metro area. So there's cars, there's power plants, there are other construction vehicles, and so we have this ratio. It's called an emissions ratio. It's NOx to CO2 emissions ratio, and we can then use that to convert from NOx to CO2. So here's NOx, nitrogen dioxide emissions. And here's the dotted line here is what's reported by the EPA, and the black is reported by my analysis. And there's going to be some discrepancy. There's a lot. This is using an older satellite data set, which has a little bit more noise and is not as highly calibrated. But I think the interesting part here is to see where there are large discrepancies. So here, there's some differences, but it's really within the error of the analysis. But in this particular time frame, that's where we think that the satellite data can be really helpful in suggesting, we really need to relook at the emissions inventory in the 2011 to 2014 time frame to see is the EPA doing this correctly. And this is more my opinion here is I don't think that the EPA really accounted for the uptick since the recession. So we know the recession occurred in 2009, 2010, and so that's why we're seeing this decrease. And then we see an increase due to the economy coming back to a higher level, and then we see an increase in NOx, but actually the EPA is suggesting that the NOx is going down. So I think this is an area where the satellite data can be really helpful is determining where there are large discrepancies. And so it's not only in the NOx data set, but also in the CO2 emissions data set. And so that's really the important part here, is to show that the estimating the NO2 from the satellite data can be helpful for not only NO2, but also for quantifying our emissions of carbon dioxide from cities. All right, so this is my last slide on NASA satellites, and I'll show you, there's some more NASA data in a second, but there's a new NASA satellite that's going to be launched in about 2 years now called TEMPO, and this is going to be, it's going to have a swath across the entire United States, and it's going to take measurements at least once an hour, if sometimes more often than that. And this will be able to show the emissions throughout different hours of the day. So the previous satellite that I was talking about just takes a snapshot in the early afternoon. This is going to take a snapshot at the very early morning hours as well as the late evening hours. And so we're going to have a nice quantification of this pollutant of NO2 from during all hours of the day, during every day. And this is great for a number of reasons, but actually I think the biggest reason is due to clouds. So in the mid-afternoon is really when we get a lot of clouds around here, especially during the summertime, and so that obstructs an accurate retrieval. And if we get, say, a retrieval at 12 p.m. when there aren't quite as many clouds, this can really be helpful in getting data every single day. I just also want to quickly mention GEMS, which is being launched by the Koreans, and which is nice because not only is it going to get Korea, but it's also going to get all of China and some parts of India as well. So a lot where the air pollution is really bad, we're going to get some daily estimates or hourly estimates from that satellite. So that, I think that's being launched either next year or in 2020. All right, so NASA is mostly, you might think of NASA as launching, well, humans into space or satellites into space, but actually NASA also flies aircraft to essentially simulate satellite data. And so one of the biggest aircraft campaigns ever in this area was called Discover AQ. Did I put the acronym on there? No. But it's deriving something from air quality. That's the T in the air quality, so you know the first and the last. Anyways, the red is actually the flight path over the area. So they flew this airplane called the P-3B. It's about the size of a 737 aircraft, and it had at least 20 different instruments on the plane, and it also flew a couple other smaller aircraft at higher altitudes. And so the red is the simulating the flight path. So it actually did what's called spirals over individual locations to quantify how much pollution is within the column of the satellite, the column of the atmosphere, to simulate a satellite data set. And it did that for several locations, and they had lots of ground monitors. Let's see what else. There's a whole array of things going on here, but I'm actually going to focus on this part right here, the ship. And so it's really, they're really wanting, one of the research questions, they have many research questions, but one of the research questions is how well do satellites observe pollution over the oceans, in this case the Chesapeake Bay, because we don't have any monitors just sitting out in the Chesapeake Bay. So we really want to know, is the satellite data accurate over these regions? We have models that predict air quality. And so these models, I ran one of these models during my graduate school time, and these models predict higher pollution over these inland water bodies. So for example, Lake Michigan, Lake Erie, Long Island Sound, and the Chesapeake Bay. All air quality models are that can resolve these small features are showing higher ozone concentrations, so worse air quality over these water bodies. And is this actually true? There are actually very few studies, if any, that actually went out with a monitor to these areas. So I was on the ship that took these measurements. So we were based out of Annapolis, Maryland, and we went on day cruises, so it sounds more glamorous than it really was. But every day we'd go up and down the Chesapeake Bay. It's pretty hot and humid during the middle of the summer, and we quantified air pollution. And so the black bar here is what we found from the boat, and the red bar here is the closest site, which is generally about right there. And let's see, yeah, there it goes. We found this was actually only 10 days. There's only so much funding to go around, so we only did this for 10 days. But during this 10-day period on land, which was just out over here, there was no days where it exceeded the air quality standard. But just over this is 10 kilometers maybe, 10 kilometers away, there were actually 4 different days where the air quality is exceeding the standard. So this is very clear evidence that the air quality is consistently 10, I'll just do some percents for you, it's about 10 to 20% higher over the Chesapeake Bay versus over land. And so this is really the first study to quantify this for this particular region, for the Chesapeake Bay. Interesting, I'm getting a little bit into the science here, but I think this is interesting. Why is this the case? And it's actually due to this discrepancy during the afternoon. So during the morning, the actual production of the air, as you remember, ozone is a secondary air pollutant, so it needs to be produced in the morning. So it's produced in the morning with sunlight and the emissions, and then around 2 to 4 p.m. in the afternoon, there's a very clear divergence. So in the land areas, the air quality gets better very quickly around 4 to 5 p.m., but over the bay it just stays throughout the evening hours. And so if you remember, the standard is an 8-hour average. So if we take an 8-hour average of this versus an 8-hour average of the bottom line, we're going to get very different values. And so, yeah, I've spent reasons trying to quantify reasons why is this happening. So again, it's been confirmed, but the reasons for this high anomaly is actually, there's 3 main reasons that we hypothesize, and there's been work since that's confirming this. But first is the weather conditions. So I won't get into the details here, but there's specific weather conditions that occur over the Chesapeake Bay, such as more sunlight, that cause the ozone to be produced more rapidly. Another reason is that there are slower removal rates. So I mentioned earlier on is that ozone can be removed by sticking to plants. And so when there are no plants, then the ozone will just stay in the air longer. And then also another thing that's really been being investigated currently by the Maryland state government is quantifying emissions from ships. Both long traveling, trips that are going out to the ocean, but also ships like recreational vehicles, what they call recreation marine vehicles. So obviously, these small boats, but also fishing and crabbing boats. And why is this important? Well, I think it's pretty obvious why this is important. A lot of people hang out during on the Chesapeake Bay or on the Chesapeake Bay beaches during the summertime when this is the problem. So this is really an issue, and this is the issue actually that's causing Maryland to be in non-compliance of the air quality regulations. So the Maryland state government has put a lot of funding into trying to investigate why this is occurring and how we can remediate it. All right, one last thing is that NASA satellite data can be helpful for assessing how well model simulations are doing. So remember the aircraft were flying around across the Maryland area, and we can use this model to then train the model to make sure that it's running properly. And we've done that, and I'm going to skip over that part here, but a little bit. But then once we have that model trained, we can then see how well is the model simulating pollution, in particular tracking that pollution from state to state. So again, I want to emphasize this. Ozone is a secondary air pollutant. It reacts it is formed in the atmosphere, and then it stays for a long time, or a relatively long time, long enough to transcend state borders. So for example, the air pollution from Ohio will certainly make it to DC, same with Pennsylvania, but if we say Maryland, will certainly affect DC, but it will also significantly affect Delaware and New Jersey. So it should be pretty obvious, but we can't control air pollution on a state-by-state basis. This needs to be a federal, but even also global initiative to control air pollution. And because there can be non-trivial interstate transport or inter-country transport of pollution. Another cool thing about the model that I've been using is it can actually track individual sectors. So that was something I was alluding to before, where we really want to know which different sector of the economy is contributing to our air pollution. So here there's some terms here which I'll clarify. So the top is what they call on-road and off-road. So these are any type of vehicles that are driven. This would also be any type of construction vehicle that's driving off-road. And so that's, according to the model, is the largest contributor to our air pollution in this area. Then we also have what's called non-road sources. So that would be like a lawnmower, or actually in this case, what's pretty obvious here is the recreational marine emissions here. So that's contributing a substantial fraction. And then also we have power plants. So the power plants, their stacks are pretty high, so they actually have a longer lifetime of their emissions. So the ozone that's attributed to these power plants can be over a much wider extent. So it's kind of smeared as opposed to something like vehicles, which the emissions are closer to the surface and affect relatively more local sources. All right. So here's just a snapshot for the Maryland area. One particular site is in Edgewood, just about 30 kilometers northeast, or 20 miles northeast of Baltimore, along the Chesapeake Bay. So this is where the air quality is the worst actually in this entire region. And we can quantify here what's going on, so which sources, but also which states are responsible for pollution. So the black bar is essentially the natural sources. This is what's coming into our model domain, as well as some biogenic sources. So that's quantified about 30 parts per billion over an average of 90. So approximately 30 to 40% of our pollution essentially cannot be controlled. But that means 60 to 70% of the pollution can be controlled. And which sources do we want to go after? Well, it's pretty clear from this that we want to go after the cars and the power plants, but also the other sources are non-trivial. So it just shows, it gives regulators a very good visual of where should we go after our pollution. For example, Maryland's state regulators would be really interested to know that cars in the state of Maryland are about 10 parts per billion of 90 parts per billion, which is a non-trivial fraction. So controlling emissions from cars is definitely going to be a good strategy to reduce our air pollution. There's some other strategies that maybe wouldn't be good to control our pollution. Some of these smaller point sources, they're important, but it might not get a great bang for the buck if they're going to control some of these smaller sources. So it's really helpful in prioritizing where to go to. Last but not least, and from a policy aspect, we really want to know which pollutant to control. So as I alluded to before, there are NOx, but there's also VOC, so nitrogen oxides or volatile organic compounds that can be controlled in order to reduce our ozone. And what's very interesting about ozone, it has very non-linear, and you can see this is not a straight line. It's when you have very high concentrations of both of say NOx, but only low concentrations of VOCs, you actually, for every NOx molecule that you take out of the atmosphere, you will actually get worse air quality versus a very, very high concentration of NOx. Of course, that's not good because NOx, as Susan has shown in her papers, causes pediatric asthma amongst other things. So we don't want to do that. But this really is helpful in showing where along the curve, which pollutants do we want to control, and how quickly do we want to control them. And so it's really important to know where on this curve, anywhere in red, this is kind of showing for the next slide, anywhere in red means that NOx is going to be the only pollutant that you want to control. Anywhere in blue, you want to control both NOx and volatile organic compounds. And so that's what I'm showing here, is that anywhere in red, you want to control just the NOx, and anywhere in, well, green or blue, you want to control NOx and VOCs. And so this is really helpful for the state regulators in showing that, say, a policy to reduce both NOx and volatile organic compounds in Virginia, for example, especially southwestern Virginia, will not be helpful whatsoever, versus a policy to reduce NOx and volatile organic compounds in Baltimore will be helpful. And so that's really what this image is showing here, and this has been very helpful to state regulators. All right, so some conclusions here of what I've talked about here. So using NASA satellite data to derive air pollutant emissions from large cities and large power plants is possible, and it's actually very well vetted by scientific literature. I'm building upon many other studies here in what I've shown. But I think what's really exciting is that these new satellite instruments, they give us the capability to develop emissions estimates from these smaller sources and for shorter time frames. So in particular, I was only averaging over a few months here, and we were able to estimate NO2 concentrations versus if we use an older satellite data, we'd need to use about 3 years worth of data to get the same data. So again, because of the missing clouds and also because of the larger pixels of the older satellites. When air quality monitors are trained by observations, especially NASA observations, these can be very helpful in constraining the model so that it can be useful in providing insight on sources of pollution, such as power plants and cars. And then finally, I think this is an interesting anecdote or interesting point for this audience here, is that the worst air quality in our area here is actually in the Chesapeake Bay region, and specifically the worst ozone. The ozone is currently the pollutant that is causing this area to be in non-compliance with the federal standards. Although, as Susan would certainly point out, just because if we're below the standard doesn't mean there's no health effects from these pollutants. So it's important to note that this is the worst. This is what's causing the states and the area to clean up their pollution, but it's good to do that. And there's many health benefits from cleaning up our pollution that are extend well beyond getting an attainment of the ozone standard. All right, so thank you very much.